Welcome to the next video on theory of machines. In today's lecture, we will see the analysis of clutch based on the uniform pressure theory and uniform wear theory. In the previous lecture, we have already seen about the construction and working of the clutch. As we have seen in the last video, that the torque that can be transmitted by the clutch is given by mu F axial into Rm into N, where mu is the clutch lining friction coefficient, F axial is the axial force that is applied on the clutch plate. It is the force by which the clutch plate remains in contact with the flywheel. Rm is the mean radius or the average radius, and N is the number of friction surfaces or the number of discs. The torque that can be transmitted by a clutch is a function of its geometry and the magnitude of the actuating force applied, as well as the condition of the contact prevailing between the members. The geometry means the dimensions. What will be the inner radius and the outer radius? Similarly, the magnitude of the actuating force, that means the axial force, which is applied to keep the clutch plate in contact with the flywheel, and also the contact prevailing between the members, that means depending on the clutch lining friction coefficient. The applied force can keep the members together with a uniform pressure all over its contact area, and the consequent analysis based on uniform pressure condition. However, as the time progresses, some wear takes place between the contacting members, and this may alter or vary the contact pressure appropriately, and uniform pressure condition may no longer prevail. Hence, the analysis here is based on uniform wear condition. So the analysis of clutch will be based on either uniform pressure theory and uniform wear theory, depending on the condition of the clutch. If the clutch is new, then the pressure will be distributed uniformly throughout the friction lining. But if the clutch is old, then the wear will take place. So uniform wear theory will be applied. Let us see the elementary analysis first. Let us consider a clutch plate with friction lining. So this is the clutch plate and these are the friction lining. This is the side view. Let us draw the front view. This is the outer radius R1 and this is the inner radius R2. And suppose we consider a elemental area, circular elemental area at the radius R and of thickness dr. Then we will see the effect on this elemental circular area, and then we will integrate for the total area of the friction lining, that is from R2 to R1. Now R1 is the external radius of the friction lining on the clutch plate, and R2 is the internal radius of the friction lining on the clutch plate. You can see here in this figure. F axial is the axial force applied on the clutch plate. Mu is the clutch lining coefficient of friction. P is the intensity of pressure, and Tc is the torque transmitted by the clutch. This axial force will be acting in this direction, in the normal direction, right? So this axial force will be applied due to the diaphragm spring, which is actually keeping the clutch plate in contact with the flywheel during the time of engagement. And due to that axial force, this pressure will be applied on these friction linings. Now, let us consider this circular ring of radius r and thickness dr. In the area of this circular ring will be 2 pi r into this thickness dr will be the area of the circular element. Next, the axial force on this circular element will be area into the pressure. So P is the pressure we have considered and 2 pi r dr is the area. So the axial force will be P 2 pi r dr. Now the frictional force on the circular element will be axial force into the coefficient of friction. So dF will be equal to mu P 2 pi r into dr. Now the torque that can be transmitted by the elemental area is equal to the frictional force times the moment arm about the axis. That is, this is the axis, the moment arm is R. That is the radius R. So the torque, frictional torque transmitted by the circular element is given by dt is equal to mu p 2 pi r dr. This is the frictional force into this moment arm. That is R. So finally we are getting dt is equal to mu p 2 pi r square dr. Now this is the elementary analysis. Moving ahead, let us first consider the uniform pressure condition. For the uniform pressure condition, the pressure at all the points in the friction lining will be constant. So if the pressure is constant, then we can directly say that the pressure will be equal to the axial force applied divided by the area of the friction lining. That will be, this will be area of the outer circle will be pi r1 square minus the area of the inner circle pi r2 square. So this will give you the area of the friction lining. Now integrating the axial force or the normal force between the limits of the inner radius r1 and the outer radius r2, we get the actuating force that need to be applied to transmit the torque. So total axial force applied on the clutch plate will be integration of r2 to r1 p 2 pi r dr. So p is constant, so we'll take it outside. So p into 2 pi will be taken outside. So it will be integration from r2 to r1 r dr. So integration of r dr gives us r square upon 2. Putting the value of limits r1 and r2, we get the total axial force applied on the clutch plate as pi p r1 square minus r2 square. Right? Now the total torque that can be transmitted is obtained by integrating the equation of dt by the limits of inner radius r1 and the outer radius r2 as follows. The total torque transmitted by the friction surface T is equal to integration from r2 to r1 mu p 2 pi r square dr. This was the equation of dt. So again 2 pi mu p is constant, so it has been taken outside, and integration of r square dr will be given as r cube upon 3. So putting the values of limit, we have the total torque transmitted by the frictional surface in case of uniform pressure condition is 2 pi mu p r1 cube minus r2 cube upon 3, which is equal to 2 pi mu. By keeping the value of p from this equation, p is equal to f axial upon pi r1 square minus r2 square. We have the total torque transmitted by the frictional surface as 2 by 3 mu f axial r1 cube minus r2 cube divided by r1 square minus r2 square, as you can see from here. This can be further written as the generalized equation T is equal to mu f axial into Rm, where Rm is equal to this remaining factor, that is Rm is equal to 2 by 3 R1 cube minus R2 cube divided by R1 square minus R2 square. So this is the total torque transmitted by the frictional surface, right? Next, let us see for the uniform wear theory. Now, according to some established theories, the wear in a mechanical system is proportional to PV factor, where P refers to the contact pressure and V is the sliding velocity. Based on this, for a case of a plate clutch, we can state that the constant wear rate Rw is assumed to be proportional to the product of P into V. So Rw is proportional to PV, and that is constant. And the velocity at the point on the face of the clutch, V is equal to R omega. Assuming constant angular velocity, we can write that P into R is a constant. Suppose it is C. Now again, the total axial force applied on the clutch plate can again be calculated as previous by integrating the dF from the limits R2 to R1 as follows. So F axial is integration of R2 to R1 P 2 pi R dr, which will be equal to R2 to R1. Now we can keep the value of P from here as C upon R. So 2 pi R dr. Now C is constant, so we will take it outside. 2 pi is constant, so we take it outside. Then R and R cancel out. So integration of dr is r in the limits r1 to r2. So we'll keep the limits. So we get total axial force applied on the clutch plate as 2 pi c r1 minus r2 in case of uniform wear condition. Next we'll find out the total torque transmitted by the frictional surface. So T is equal to integration from r2 to r1, as we have done it previously, mu p 2 pi r square dr, this is dt. So this will be again equal to, we'll keep the value of p here again. So r2 to r1 mu c by r 2 pi r square dr. R and r will be cancelling out. We'll take out 2 pi mu and c as constant. So we'll take it outside, and integration of r will give us r square upon 2 in the limits r1 and r2. So this will finally give us T is equal to 2 pi mu c r1 square minus r2 square upon 2. Further, taking the value of c from this F axial equation here, so c will be equal to F axial divided by 2 pi r1 minus r2. So keeping the value of c from here in this equation, we get total torque transmitted by friction surface as 2 pi mu F axial upon 2 pi r1 minus r2 into r1 square minus r2 square divided by 2. 2 and 2 will cancel out, pi and pi will cancel out. So finally the total torque transmitted by the friction surface in case of uniform wear condition will be mu F axial r1 plus r2 divided by 2. So again writing this in the generalized form, we have T is equal to mu F axial Rm, where Rm is equal to R1 plus R2 divided by 2. So this is how we calculate the total torque transmitted by the frictional surface in case of uniform wear condition. Now let us find out the total torque transmitted by the clutch plate. The total torque transmitted by the clutch plate, as we have seen earlier, is given by mu into F axial into Rm into n, where n is the number of frictional surfaces. For single plate clutch, n will be equal to 2, and similarly for the multi-plate clutch also n can be calculated. Now this Rm, this equation will be same for both the conditions, uniform wear condition also and uniform pressure condition also. Only the value of Rm will be different. So the value of Rm in case of uniform pressure condition is given by Rm 2 by 3 R1 cube minus R2 cube divided by R1 square minus R2 square, as we have derived earlier. And similarly for uniform wear condition, Rm is R1 plus R2 by 2. So this is how we find out the total torque transmitted by the clutch in both the conditions of. I hope you have understood the derivation, and in the next lecture we will apply these equations to solve the numerical problem. Thank you.